Today's topic is circular motion, and in particular, circular motion in the context of Newton's second law. As we get started, let's go back to our talks on kinematics, where we talked about the position, velocity, and acceleration vectors. The velocity vector tells us how fast and in what direction the object's going. The length of this vector gives us the speed at some moment, and the direction is in the direction of the velocity vector. The acceleration vector is the time derivative of velocity. It tells you how the velocity vector is changing. So in this case, this object would be speeding up. It has a velocity vector in this direction, and the acceleration is in the same direction, so this vector is going to get longer. If the acceleration vector was opposite that, so that it looked like this, the object would be slowing down. The vector is this long, but it's changing this way, so as time goes by, it'll get shorter. The component of acceleration parallel or anti-parallel to the velocity changes the object's speed. It doesn't change the direction. On the other hand, if there's a component perpendicular to the velocity, like this, that component will change the direction without changing the speed. In this case, this velocity vector would rotate to the left. Now let's apply this to the case of an object moving around a circular path in what's called uniform circular motion. When we say uniform circular motion, we mean circular motion when the velocity vector has the same length, when the object's going at constant speed. That's the uniform part of it. Uniform means moving along the circular path at constant speed. So let's draw a circular path and imagine an object as it travels around this path. At this point, it would have a velocity vector this way, always tangent to the path, and the length of it tells us the speed. Later, the velocity vector is going to be this way, tangent to the path, and then over here it'll be like this, always tangent. And I'm trying to draw these vectors with the same length to indicate that the speed isn't changing. Now, if the speed isn't changing, we know that the acceleration must be perpendicular to the velocity. If there was a component parallel or anti-parallel, the speed would change, but it's not, so the acceleration must be everywhere perpendicular to the velocity. At this point, the acceleration has to be either straight in towards the center or straight out. And we can see, because this object is turning to the left, something has to push this velocity vector this way to make it stay on this circular path. Here, it gets pushed this way. Here, it gets pushed this way. Here, it's pushed this way, so that this vector tracks this circular path. The acceleration vector is always straight in towards the center. The velocity vectors are all in the tangent direction. So these acceleration vectors, which have to be totally perpendicular to them to keep the speed constant, must be in the negative radial direction. They have to be pointed to the very center of this circular path. So some things we can conclude so far about the acceleration vector in the case of uniform circular motion. We know that the acceleration must be perpendicular to the velocity because the speed isn't changing. We can also see that that acceleration vector must be directed toward the center. So the acceleration vector always points toward the center of the circular path in the case of uniform circular motion. You can work out what the magnitude of this acceleration vector is. I'm not going to derive it for you here. There are many derivations. You can find them in almost every physics book. You can find them all over the web. I have a colleague at work who's compiled a set of all the different derivations he's come across for the magnitude of this acceleration. He has 6 different ways of doing it. Go check it out. What you find is that the magnitude of this acceleration, I'm going to call it A sub c, I'll tell you what that c is in a minute, equals v squared over r, where v is how fast the object's moving, and r is the radius of the circle. So that's r right there. Okay, this c stands for centripetal. Centripetal means center seeking. So this is the center seeking acceleration. It's the acceleration that makes this velocity vector track on that circular path. And it's called center seeking because it always points directly to the center of the path. All right, so when we are solving problems involving circular motion in the context of Newton's second law, when you find something moving in a circle, you know that there's going to be an acceleration along the direction toward the center of the circle. The magnitude of that acceleration is going to be v squared over r. And that means there must be some net force directed to the center of the circle. There might be one force that's pushing the object to the center. There might be two forces. There might be three forces. There might be many forces whose net effect is to push the object to the center. But if you have something moving in a circle, you can be sure that there's going to be a v squared over r acceleration toward the center, and that therefore there will be a net force in that direction. Let's look at several cases and talk about what force or what net force is responsible for moving the velocity vector and rotating it toward the center. I'll show you several cases and then we'll work through a couple in detail. Let me erase this stuff so that we have room to draw some new pictures. I'm going to leave that so that we can remember what the centripetal acceleration is. Let's move it up here. All right. As a first example, let's suppose that we are standing here and we have a string with a rock tied to the end of it, and we're going to swing it around over our head along a circular path. So here we are. I'm holding a string in my hand, and I'm going to swing this string around in a circle so that the path of the rock looks something like this as it flies around in a circular path. I know as the rock is moving around that everywhere the acceleration is toward the center. I'm going to draw these orange vectors but not write all the A's. Okay, so there's always an acceleration toward the center. That acceleration in this case is coming from a force that's caused by a component of the tension. The string that's attached to the rock is always pulling the rock in toward the center of the circle. That's why the rock goes around in a circular path. There's a component of tension that's making it move in a circle. Here's another case. Suppose you are washing your clothes and it comes time to dry them, and you put your clothes in a dryer that looks like this so that it's going to spin around this axis and most of the water gets sent out. So this drum of the dryer is going to spin around and pin some clothes to the side of it. If you've ever opened up a dryer, you find things stuck to the outside. So this might be a sock. It's stuck to the edge of the dryer here. So as the dryer turns, the sock is going to travel in a circular path around this way. Travel around like that. We know the acceleration is going to be directed towards the center. And the question is, what force, or what net force, is pushing the sock toward the center all the time? And the answer in this case is, there's a normal force. The wall of the dryer is pushing on the sock, and it's going to push it straight in. And that normal force is what's responsible for making the sock move in a circle and give it that centripetal acceleration. Here's another case. Suppose we have the sun with a planet orbiting around it. So here's a planet, it could be Earth, moving with some velocity v this way, but instead of going in a straight line, the planet moves in a circular path. That's a terrible circle, but let's imagine that's a circular path. There must be some force making this planet accelerate towards the sun. So what is the center-seeking force in that case? What is the force that's giving it this orange acceleration? Well, in this case, it's gravity. In each of these cases, the force that's giving us this orange acceleration vector is what we call a centripetal force. It's simply a force that gives us a centripetal acceleration. It could be one force, it could be a combination of forces. But whatever net force is directed toward the center making the object accelerate that way, is what we call the centripetal force. Here's a case where more than one force combines to give us a net centripetal force. Suppose instead of swinging the rock around in a horizontal circle this way, suppose we swung the rock around in a vertical circle. So the path looked something like this. When the rock is at the bottom, the string would be down here, like that. When the rock's at the top, the string would be up here. Now in this case, the acceleration is still always directed toward the center, but there's more than one force giving us that centripetal acceleration. At the very bottom of its motion, if we drew a free body diagram there, let's just draw one, we would ask ourselves, what forces are acting on this rock at this point right here? There are two. The rock has mass, so it has a weight going down, and there's a string tied to it, so there's a tension pulling up on the rock. If I added those two forces together, that net force would give me an acceleration toward the center of the circle, so that T minus mg would be the centripetal force in this case. The important point here is that if you have an object with a centripetal acceleration, an acceleration toward the center, there must be a net force toward the center. And that net force sometimes gets referred to as a centripetal force. It could be one force, it could be a combination of many forces, but there has to be some net force towards the center. Whatever those forces are, we can call them a centripetal force. Okay, let me stop this one here, and I'll show you an example or two of how we apply this in particular to the context of Newton's second law.